Okay, so good afternoon in the first place. Let me welcome you to the webinar on transmission and distribution expansion planning. My name, as you see here, is João Tomé Saraiva. I'm sharing this webinar. I'm with the Electrotechnic and the Computers Department of the Engineering Faculty of Porto University in Portugal, and with the Power Systems Center of INESC TEC, which is a research institute associated with the University of Porto. So today we have large amount of people registered to this webinar, I think from 165 different institutions, which demonstrates the interest and relevance of expansion planning issues associated both with transmission and distribution networks. And this is certainly due to a large number of reasons, namely the massive integration that is expected in the next few years of electric vehicles, the connection of increasing amounts of renewable generation, in some cases directly with the transmission networks, namely large wind and PV parks. And of course, also the possible impact that these reinforcements and expansions and investments will have on the tariffs paid by end consumers, namely the use of transmission and distribution tariffs. So to help us understanding some of these challenges and these issues, we have with us today Nuno Fidalgo, that I will introduce afterwards, and also Luis Oliveira, who will be the second speaker. So we'll be having two presentations in sequence, and after those two presentations, we will have a 30-minute of question and answer period. So I invite you to write your answers on the question and answer facility. I will read the questions, and then they will be answered online by the two presenters. So going to the first presenter will be Nuno Fidalgo. We'll be speaking about distribution network reinforcement, how valuable is the investment postponement, and some words about Nuno Fidalgo. He obtained his licentiate degree in 1984 in electrical engineering and computers at the Faculty of Engineering of Porto University, where he also obtained his PhD in 1995, and currently is associate professor since 2011. He is also the coordinator of the Energy Analytics and Forecasting area of the Power Systems Unit of INESC TEC, and he participated in more than 50 national and international projects. His research interests include load profiling, loss analysis, distribution planning, data-driven and machine learning technique applications to power systems. So now I will interrupt sharing this PowerPoint, and I will give the floor to Nuno Fidalgo. Okay.
Okay, thank you. Okay, are you seeing my screen?
We are.
Okay, thank you. Well, good afternoon and welcome to this webinar. My name is Nuno Fidalgo, and my talk is about network reinforcement and how far should we go in grid upgrade postponement. We start this presentation by presenting the motivation behind this research. Then I will pass to description of the work. In the first part, we will compare a traditional network upgrade with an optimal one. And in the second part shows how to find a practical criterion for network upgrade. Finally, the main results obtained and corresponding conclusions. So what was the motivation for this work? Well, we saw lots of papers claiming that smart grids allow a deeper exploitation of existing infrastructures and saw considerable savings in network reinforcement. Well, when we were involved in the CityNesh project, one of the tasks was exactly this part demonstrate this, but in fact, part of our results did not agree with this second part. So we thought we need to go deeper in this research. Now, let's start to imagine a future perfect smart grid with omnipresent monitoring, reliable communications, distributed processing everywhere, and advanced control abilities. These features will allow a deeper integration of renewable, consumer participation, better control of demand response, electric vehicles charging, storage, etc., etc. So many researchers conclude that these features can make the flow diagram flatter, allowing the postponement of investments in grid infrastructure. For instance, let's consider a demand response program designed for peak shaving. So it says we consider it works perfectly. So this will allow the postponement of investment in grid upgrade. The question is, how valuable is upgrade postponement? Should we always do it? Let's see what we found. Well, in the referred CTNASH project, and in order to analyze this question, we adopt a INESC approach where several combinations of microgeneration, demand response, EV in terms of growth and charging times and load growth were considered. So lots of scenarios were considered, and other simulation parameters such as discount rate that is necessary for long-term economy appraisal, energy costs, and so on. The next phase is power flow, so to simulate the network and all those conditions, and this was repeated for a time period of 20 years. In parallel, we also compute the costs, characterized in terms of net present value, and these costs include the investment costs for enforcement of lines and transformers, operational costs, and also amortization costs for a time span of 20 years. So for illustration purposes, let me just show two types of scenarios for microgeneration PV and for electrical vehicles. When we first were involved in this project, we borrowed these projections from official entities, although, as you know, there is always a big level of speculation. But in any case, there are scenarios. For instance, electric vehicles, we have two growth scenarios and three basic charging types: non-control, dual tariff, and smart charging. And of course, according to the electric vehicles dissemination, according also with the charging type, they have different impact in the load diagrams. In what concerns the reinforcement procedure, we developed an approach in the framework of a project with a Portuguese DSO. The first step consists in setting a criterion for starting the upgrade. In this example, it is when the peak of the diagram reaches 80% of the maximum capacity. Suppose it is a line. When it reaches 80% of the line maximum capacity, we start the upgrade procedure. In practice, this criterion might be combined with other drivers, such as some quality of service index also, but let's forget this for the moment. Then, for a set of available cables, consider these are the available cables. We must choose the feasible ones. And by feasible, we meant, for instance, if the current line is a 70mm cable, we cannot replace it with a 50mm one because it will have a smaller capacity. So for the feasible solutions, we compute the total investment costs in terms of reinforcement and the expected losses for the time span of 20 years. And that allows us to compute also the losses costs. And as you can see, these blue bars represent the reinforcement costs, and the reinforcement costs, of course, they grow with the section. So the larger the cable, the higher the costs. The losses, they vary in the opposite direction. So the larger the cables, the lower the costs. And we should compute all the case for all solutions, combine these costs, including the amortization costs, and at the end, we choose the solution with the lowest cost. In this case, it will be this one. So we applied this in the scope of the INESC project, and let me show some results. Several scenarios are considered here, 18. In this table, the first column is just identifies the scenario. The second column is the demand response level. 0% means that no response, no demand response is considered. 3 and 5% are related with the amount of energy that is shifted from the peak. And of course, this is repeat 0.35, 0.35%, and so on. Third column is the PV scenario. 3 are considered in this case, PV 1, 2, and 3. It's not important for these examples to know exactly which scenario, what represents each PV scenario. And in terms of electric vehicles, we consider the hypothesis, non-controlled charging up to here, and smart charging. So for a matter of simplicity, let's compare the green cases with the brown cases, okay? And the green cases have non-controlled charging, while the brown case, it is smart charging. The rest is equal, PV2, the scenario for PV, and the demand response 0, 3, and 5%, and the same in this case, 0, 3, and 5%. Now, let's look at the reinforcement costs associated to these cases. So again, let's concentrate in our attention in the green and the brown cases. So the first obvious conclusion and is that the demand response level, as higher it is, means that we're able to get the peak share more than in the lower levels. So it's natural that reinforcement costs decrease with as long as we get more of the peak. And that is true both for non-controlled charging as well as for smart charging. We also see that the costs for smart charging are smaller than the costs for non-controlled charging. So this is natural because, as was expected, the smart charging allowed to avoid some part of some charging during the peak hours. So it's the same reason that is behind is the same kind of factor that affect the diagram. So these are more than expected results. Now let's see the other face of this coin. So if we compare the losses of the non-controlled charging with the loss of the smart charging, we see that non-controlled has smaller losses than in controlled charging. So this is natural because as this reinforcement, the reinforcement level for non-controlled, as is higher, we probably will have lines with larger section, and so the losses will be smaller. Now, let's look at the total costs. So when we aggregate the costs of reinforcement, the cost of loss, and the corresponding amortization costs, we obtain these figures. Again, we see that in general, the smart charging has lower costs than non-control charging, but this is not always true. Just compare the A6 case with the A15. In this case, the cost is lower. So, in fact, what we can conclude that there is a trade-off between saving in investments for reinforcement and or saving in avoiding losses. So in face of the previous results, we thought we should try to find an optimal reinforcement strategy. And that's what we implement, in fact. So you use an evolutionary algorithm, and the objective function was to minimize the total cost in the 20-year period. So this is quite time consuming. So we need to consider several simplifications. One of them is to reduce the number of scenarios. For this case, let's just consider these 4 scenarios. These scenarios are the combination of 2 network types, let's say. One, smart grid, where we can perform demand response, smart charging of electric vehicles, and so on. And a non-smart grid, one where none of these things can be done. And these network cases are combined with the traditional upgrade, that was what was used in the previous study, with an optimal upgrade that will be provided by the evolutionary algorithm. So, some more simplification. Very simple networks. One of them is the most simple one you can imagine. It's very simple, but is important as a proof of concept. And we also, for reinforcement, we only consider line doubling. That is, whenever the reinforcement is to be applied, we consider just the installation of a similar line in parallel with the existing one. So the resistance, total resistance will be half of the original one, and this simplifies a lot the process. Yes, we know that this is not according to practice, but it will be enough as a proof of concept, as we will see in the next slides. So let me amplify this for you. So these are the results in terms of upgrade costs or reinforcement costs. And here we have the cases. This case are no smart grid traditional upgrade, no smart grid optimal upgrade, and the same for the smart grid traditional and optimal. Let's concentrate in the optimal upgrade case, so the green and the blue bars. So note that green and blue bars are all in the first years. So in fact, the optimal upgrade anticipates the reinforcement, while the other case, they are activated when they reach, well, the peak of the diagram reach 80% of the maximum capacity. The optimal upgrade says we should upgrade as soon as possible. This might be a bit strange, but we'll just see in moments what are the consequences of this. Another conclusion is that optimal upgrade is much more expensive than the traditional upgrade. For instance, compare the red bars with the blue bars for the smart grid case. Traditional upgrade here, we had a bar we would spend 100,000 euros in this reinforcement, while with the optimal upgrade is 100,000 plus 200,000. So it 3 times, we will spend 3 times more with optimal upgrade than with the traditional upgrade. Okay, now let's see the other face of this coin, losses. When we look at the losses, we see the opposite. That is, the optimal upgrade, again, the green and the blue bars, are at much lower losses than the traditional upgrade, both for smart grid or no smart grid. So the green and the blue bars are always below the purple and red. So the losses are pretty high when in the traditional upgrade when compared to the optimal upgrade. So now let's look to the total costs. When we join all the costs, including the amortization costs, we see that an optimal upgrade at much less lower cost than the traditional upgrades, both for smart grid or no smart grid cases. And we see also that being the network type, no smart grid or smart grid, well, the costs, I would say, are very alike, are comparable. So these results are for the network one. Remember, it's just one line, okay? Now let's see what happens in the network two. Well, for the network two, the conclusions are pretty similar. Again, most of the reinforcement costs are in the first years, okay? And if you compute the total costs with optimal upgrade rule, they are bigger than the cost with the traditional upgrade. And again, the losses for the optimal upgrade are below the losses of the traditional upgrade. When we compute the total costs, we obtain very similar results. Again, the optimal upgrade shows quite smaller costs, about 20% less than the traditional upgrade. And again, we have the smart grid and no smart grid and smart grid with similar total amount, total cost. So there are lots of conclusions, but I would say that main conclusion is the postponement of grid reinforcement is not always the best option. In fact, our results show that sometimes it is better to anticipate the reinforcement. Well, our optimal upgrade approach, as I said, it's very demanding and of course is far from practical. So what if instead we try to find the most economical upgrade trigger? So we said that in our approach, we consider the trigger of 80%, but what if we consider all these possibilities from being 50, 60, 90% and choose the most economical option? That's what we did. In this case, the network test was this one. The data, I can share with you, all the data is available in our site. I can share if you are interested. The methodology was very similar to what was used in the initial study, but instead of a fixed upgrade trigger, we consider this variation, that is from 50 to 90% in steps of 10%. Now let's look at the results that were obtained. First, I will present the results with the energy cost of 101.3 euros per megawatt hour. That was the reference price at Portugal in 2016 for the medium voltage. And okay, these results are parameterized in terms of discount rate. Okay, I would say that nowadays maybe this case will be the more close to the used in projects. 5%, 6% is the most usual nowadays. But in any case, we can see that another detail is that, as like in the previous study, was made for network no smart grid, business as usual, means no smart grid, and smart grid environment, the green bars. So we can see that the lowest, the upgrade trigger that leads to the lowest cost is 60% for this discount rate. In this case is 60 or 70%, and in this case is 70%. So we know that the most economical upgrade trigger depends on lots of parameters, but always, in this case at least, it was 70% at the most, never very close to the limits of capacity, line capacity limits. Now, with the energy cost of 150 euros per megawatt hour. In fact, this was suggested by an Italian colleague because in that year, 2016, that was the price, the reference price of Italy. So with this price and similar conditions, the upgrade criterion, the best, is with 50%, and this, in this case, 60% for discount rate of 10%. So it's low. It says we should anticipate the grid upgrade. And why? Well, because with the higher energy costs, we have a higher value for the losses. So we should try to avoid the losses as much as we can. So the previous studies exemplify some cases for which it is better to postpone network reinforcement. The question is if there are some typical situations where it is advisable to postpone. We think yes, and this is an example. If we have an annual load diagram with a very high peak, very short duration, well, in this case, it will be probably better to postpone investments. Of course, if we can decrease somehow this peak or make some kind of demand response program anyhow. But note that admit we were able to shape this peak with some kind of demand response initiative. Then after this action, we would obtain a diagram that is of the kind that of the ones that were used in the previous studies. So the question is, after this, we probably would conclude the same thing. Another situation that advocates investment postponement is when the taxes, I mean discount rate, inflation, and so on, are very high. Well, in 1980s, the inflation in some European countries was above 30%. In this case, it will be probably better to postpone investment because the discount rate with the inflation of 20% discount rate will be 20 something. So the money borrowing will be very expensive. However, in the last 2 decades, as you can see in this graph, the inflation has been rather been kept in below 5%, and it is not expected to grow substantially in the next year. So I would say that conclusions that were drawn before will be valid in the next years. Jumping to the conclusions, I would say that, yes, it's true that smart grids empower the potential to postpone network investments, but this is often disadvantageous. You can do it, but you should not do it. Well, the global costs. Now, the conclusion is that the global costs depend for sure on several parameters, but we found that upgrade trigger that provides the lowest costs are between 50 and 70%, never very close to the maximum capacity. So do not exploit the network too close to its limits. Well, as a final remark, I would say that investment postponement might allow savings in short term, but long-term consequences are often costly. With this, I conclude my presentation. Thank you very much.
Okay, thank you, Nuno. Okay, we were planning to have the two presentations in sequence and then having the questions and then having some sort of debate, but you already have here 4 questions, so I perhaps would go directly to these questions and then give the floor to the second speaker, to Luis, okay? So I will read the first question from Marie-Cécile Alvarez-Geroux. Thanks for your presentation. I have several questions. The main logs for in the topic of planning with the distributed energy resources and flexibility are uncertainties. How do you model them, uncertainties, and integrate uncertainties in the planning methodology? This is one question. And then I did not see how the power system, high voltage, medium voltage, or low voltage is modeled, which is mandatory to evaluate the needs for enforcement. Can you add some explanations on the modeling of the grid?
Okay. First, let me start by saying that, well, the uncertainty is somehow represented by the variety of scenarios that were considered. So we don't know how let's say, how the electric vehicles will evolve, but we can consider several kinds of scenarios and check the results for those, check the results. And what we saw was that as a general, these results that were presented are kind of typical. Yes, sometimes the costs are a bit higher, sometimes the diagram has more peaks or has a load factor, a smaller load factor, whatever. But these are, I would say, quite general. So we changed the microgeneration, we changed the storage, we changed the electric vehicles, but our main conclusion is that under the current circumstances, we should not exploit the network very close to the limits. Concerning the network, these studies concern medium voltage networks. So that's what we did. It was in the scope of our project, and it was our test set.
Let me just ask you in the middle another one, because there is a question asking if the network is rural or urban. So before going to the modeling, could you give some more details on the kind of network?
Well, one of the last network was based on the IEEE 123 test system. So it's that network. I'm not sure it can consider. I would say it's more urban because of the size and type, but I'm not sure. But generally, we apply this, at least in the scope of CityNext project, we apply this in cities, so urban, yeah.
Okay, and the modeling that was in the kind of modeling you used, I don't know what was meant by that, but perhaps in terms of flows, losses, what kind of tools you used to model the networks?
To model the network? Well, we assume we have the structure, the characteristics of the network. I'm not sure if you understood exactly the question, but in the case of the IEEE, we have the characteristics of the network. In the case of the CityNext project, we have also access to the characteristics of the network. So in terms of the loads, yes, of course, we are never sure about the loads, but we have, as I said before, we consider scenarios for the loads and variations for loads. We consider scenarios for microgeneration. We consider scenarios for electric vehicles. And of course, all of this is translated into load diagrams that somehow affect the power flows in the network.
Okay, there is another question, which is related still with the uncertainties. Are the conclusions valid in a highly uncertain environment of network usage in terms of flows not being predictable? And still related with the scenarios, all these scenarios may take a very high computation time. You must have done a lot of hypotheses to get results in a reasonable time. Don't you think a probabilistic approach would be more appropriate?
Well, considering the uncertainty, of course, we know that in practice, we don't have access, we don't know sometimes the characteristics of the network, sometimes we don't know some characteristics of the load or some characteristics of distributed generation. Yeah, of course, for that cases, we can or use some kind of probabilistic modeling or consider some scenarios. But I would say that is not too relevant because what we have shown is that if the network are exploited very close to its limits, the losses will be very high, and you should reinforce the network. You should not postpone the reinforcements because we will pay that with losses. Maybe in some cases you don't know if you are exploring the network very close to the limits, but I don't know how I don't have an objective answer and quick answer for you for this particular aspect. Yeah, I believe that maybe you need to have some look at some quality of service index or something like that to know if the network is being used with very close to its limits, for instance, voltages or losses or something like that.
Okay, now there are two questions related with the materialistic. One of them, I don't understand why you need a materialistic to solve the problem. Can you detail exactly the objective function and the constraints? And then how do you evaluate the use of materialistics in future works, I believe, in this area, in terms of expansion planning and reinforcement selection?
Yeah, okay. Well, as I said in the approach with the materialistic, in the case with the goal was to minimize the total costs. So that includes the enforcement costs and the losses costs and amortization costs. It's also important. So we implement a materialistic to decide about the best moment to reinforce and how much to reinforce each year. So that is very demanding, but the goal was not to apply that in practice because I think it is not practical at all. So that's why we propose a second study where we decide the best upgrade trigger. Because in face of the conditions, in face of the discount rate, in face of the cost of the energy, you can decide what is the best upgrade trigger. And that is very simple and in our opinion should be considered integrated in the usual tools by the network operators when they are considering reinforcement.
Okay, then there are here two comments, namely on the value of DR. One of them indicates that DR saves money, IDR saves money. Does this study provide a proxy of the value for flexibility services to help balancing the system? And then how the percentage of DR was chosen following any standard or review of state of the art? So those percentages, how were they chosen?
Well, we cannot choose the R. I mean, that TR is related with inflation rate, with interest rate, and so on. So, now you go to the bank and well, you put, let's say, 1,000 euros in the bank, and the money you receive for having your deposit there, it's quite small. Why? Because the interest rate is really small, because inflation is also small. So a few years ago, so as I said, in the 80s, 1980s, when the inflation rate was about 20%, well,
sorry,
1,000.
it was not really the R. The question was on the demand response, not the discount rate.
Okay. Yeah, I heard this. Okay. Yeah. Okay. That's yeah. In terms of the demand response, that was parameterized. So we consider several hypotheses. In these scenarios that were shown, we have 0, 3, and 5%. And that considers, in our study, we consider that the demand response will be a percentage of the load in the peak from domestic consumers. So we consider that if it is industrial, probably you won't change this usual routines. So it is a percentage of the residential peak power. And of course, it is parameterized, that if we have no clues. There are some studies, and we use the results on some studies to establish these limits, but of course we know that depends on each case. So we cannot assure that in a given country or even in a given city, the demand response will be 1% or 5% or anything else. I don't have a definitive answer for you regarding this.
Okay, just before passing to Luis, to the second presenter, let me just ask you for a quick comment. Because as you know, here, well, in Portugal, we have some sort of incentive regarding the distribution activity in terms of reducing losses. So if the distribution company manages to operate the system in conditions so that the losses in a given year is below a reference level, they will receive, let's say, a prize, and the mechanism is symmetric, they can also be penalized. The issue is, well, that could be used to induce companies to invest in terms of reducing the losses, but perhaps the unitary value of the avoided losses is not enough to pay for the extra amount of investment. That is, the trade-off is not well established. You have any idea on that? Do you think the current mechanism we have here is well designed?
Well, I think there are two levels of problems. Well, we were involved in 2011 in a project with Portuguese DSO, and the goal was, in fact, to reduce losses. And we have this kind of, the reinforcement procedure was very similar to the one I presented. And we have seen that in the end, the medium voltage, we have some cases where the payback time was 3-4 years. So if they invest in reinforcement, they will get that money back in 3-4 years. So, and the rest will be losses that are avoided. So it will be a good business case. But nowadays, I think we have our mechanism, the Portuguese mechanism for reducing losses, as some kind of limitation because of distributed generation. And distribution generation, we have some studies that show that this increasing losses and the DSO cannot control that.
So
the problem
is being penalized by something is not controlled. Is not controlling.
That's it. So that is a question that is being under discussion with the regulator. Let's see where is going to this discussion.
Okay.
Let's wait.
Okay, thank you very much. So let's now go to the second presenter. So let's share my Okay, so the second presentation is entitled Transmission Expansion Planning. So we will move from distribution to transmission, the uncertainties and the challenges, the new uncertainties and challenges, and it will be presented by Luis Eduardo Oliveira. At the moment, Luis is in Brazil. He obtained his Master of Science in Power Systems from the University of Brasilia in 2017, and then has done a specialization in the Brazilian payroll. And after graduating in 2013, he was an university professor in, I believe, Minas Gerais, Brazil. From 2014 to 16, he worked at Capgemini in a Caixa 10 project as sub-consultant. Back to engineering after his master in Brasilia, Luis came to Portugal, where he started his PhD in power systems in the Faculty of Engineering. And he also worked in INESC TEC in the Integrate project and in the V2G project development in the archipelago of Açores. And currently, Luis went back to Brazil. He's a senior engineer on Siemens. So I'm going to stop sharing this and giving the floor to Luis Oliveira. So let me welcome you. Thank you very much for collaborating with us in this webinar.
Okay, first of all, thank you, Professor Saraiva, to open this webinar for me. It was really good, the opportunity. And I want to congratulate Professor Nuno for the presentation. It was really good. So I'm not used it much with that new way to present. Based that I'm talking with the computer. I prefer when I am in the stage, talk with the people. So I decided to record my presentation. So when I share my screen, let's go. I'll try to do that. Okay.
Hello, everyone. My name is Luis Eduardo de Oliveira, and today we'll talk about transmission expansion planning and the new challenges. So transmission expansion planning basically is a problem that aims to find solutions with the most adequate cost-benefit balance. So normally the planner wants to maintain or increase the security of supply and reliability, or also reduce costs of investments, accommodating larger amount of volatility in loads and renewable generation, and also avoiding the expected energy not supplied. So the main difficulty in solving the deterministic TEP problem is related to the non-convexity of the solution space. The temporal coupling is another aspect that should be addressed. So if the planner chooses to the static TEP, he will understand the planning horizon as a single stage. However, if he chooses the dynamic TEP, he will divide the planning horizon in sub-periods. Another aspect is the combinatorial explosion of the possible solution set, leading to a mixed integer nonlinear programming. The integer variables related to the transmission components and the continuous variables related with the power flow variables. The new challenges that catapult the difficulties in TEP are related to the change in activity load patterns due to increase of distributed generation, the electric vehicles penetration, the dissemination of smart and microgrids, storage systems, and the uncertain behavior of the generation players. So low carbon energy transition is also a new difficulty in TEP problems. The growth share of renewable energy sources and also the decommissioning of coal-fired plants, the system topology has changing year by year. And the new difficulties that should be addressed are the climate changes and the weather conditions. So uncertainties should be addressed aiming at representing the networking environment as real as possible. If the ring risk is allowed into the solution space, it should be exterminated. Because the most important thing is not guessing when and which event is going to happen, but prepare it for the worst possible nightmare. Otherwise, you open windows for life-changing events, as well as Texas minor storm that happens in 2011 and Texas May or blizzard storm that happened in this year. So, so an umbrella protection can mitigate the consequences of unexpected events, turning a black swan into a gray swan. The uncertainties should be addressed aiming at representing a network and environment as real as possible. Relaxed models reduce the computational burden, but do not ensure the feasibility of their solutions to the real world. So the more far-fetched is the research, the larger mathematical burden is introduced into the problem. And techniques capable to address uncertainties and obtain better models should be addressed. The 9-Hill-22 steps is a simple and easy test that can show the necessity of representing uncertainties. So if you choose a random guy in the streets and say to him to do that test that represents 9 steps forward and 9 steps back. So if you bet in success, the odds are very high. However, when that guy appeared to do the test, he was completely drunk. We didn't know that 2 hours before the test, he was drinking with his friends. So the chances of success is still the same. After 100 tests, we see if he was sober, he could complete the test very easily. Considering that he was drunk, the blue curve on the right graph shows that his possibilities to obtain success in this test was very reduced. So at the end of the story, the bet was not so good. So uncertainties appear in power systems in many different ways, and they can be classified regarding their origin, their mathematical model, or behavior in nature. So here in this slide, we classified the uncertainties by their origin. So normally, they only consider economical and technical parameters, but the environmental parameters has become very important to be addressed with the climate change and weather conditions. If you consider to classify the uncertainties based on their mathematical model, you have 3 main groups: random, non-random, and vagueness uncertainties. The random uncertainties can be modeled as a PDF curve, as well as load, wind speed, or solar irradiation. However, the non-random uncertainties are events that change the game, as well as fail probability. Before the fail, the equipment is available. After the fail, the equipment is unavailable. Market rules, generation or substation player decision, governmental and incentive policies. So basically, non-random uncertainties are something that doesn't depend on the planner, but is going to happen and change the game. and Wagner's uncertainties represent something that can be modeled regarding the opinion of the planner. Wagner's uncertainties represents opinion that are not certain as numbers. So if you look at the sky, at the same time, at the same place, some people would say that the sun, some people would say that the sky is blue, other that is gray. If you think about a swimming pool, and I ask you which color is the water, some people should say that is transparent, other would say that is white, other would say that is blue, green. So it depends on your opinion. Related to power systems, the decision maker behavior is something that is considered vagueness. So the risk proneness or aversion related to the decision maker is something that is considered completely vagueness, requiring fuzzy logics to solve. Requiring fuzzy logics to be modeled. Another way to classify the uncertainties is related to the way behavior in the nature. So they can be classified as short-term uncertainties, long-term or mid-term. The short-term uncertainties change very fastly, day by day or hour by hour, as well as the electricity price, stock price, the demand, wind speed, and solar irradiation. However, the long-term uncertainties change with the time as the load growth, the inflation, interest rate, the wind and PV share on generation mix. The mid-term uncertainties suffers both short and long-term variations, as well as EV charging or discharging. Basically, as well as EV charging, or discharging on the network. In short term, the EV charging or discharging behaves itself as a load. However, with the time, it suffers the load growth too. So it can be considered a mid-term uncertainty. So the wind speed and solar radiation are considered short-term uncertainties because it's not possible to ensure with 100% sure how will they behave in the next hour or 15 minutes. However, year by year, they behave themselves as the same. However, year by year, they not change too much. If you consider the yearly solar radiation, it's almost the same every year. The problem is the climate change are changing the renewable source behavior. So year by year, the wind speed, the solar radiation, and hydro capacity are changing. So the main common uncertainty handling approaches are the probabilistic, possibilistic, and the hybrid approaches. The possibilistic approaches are related with fuzzy logic, the probabilistic normally with Monte Carlo simulation, scenario-based analysis with the stochastic programming, and point estimate method. Another different technique is the robust optimization that enable umbrella protection without consider a lot of scenarios. So as a test case, we proposed to test the modifier IEEE 24 bus. The modifications are related with the initial demand in each bus that is multiplied by 2, and the generation capacity that is multiplied by 3. And and an energy transition to a low carbon mix is also considered. Therefore, over the planning horizon, coal-fired power plants are decommissioned and new solar and wind farms are commissioned according to the table on the next slide. So the demand growth rate is considered as 2% per year. Okay. Okay, so we planned to decommission 3 generators. And in parallel, we'll insert 8 generators, 4 solars and 4 wind farms. The first case study is the T24, the deterministic approach over the IEEE 24 bus. So in this test, we planned to insert 1 cable and 1 line, and these two equipment represents an investment of $137.63 thousand. However, when we consider uncertainties, we inserted short-term uncertainties related to the demand and PV and wind generation. We also addressed long-term uncertainties with the load growth. In the case study S24, we did an stochastic approach over the IEEE 24 bus system. The most important thing in this table is related to the investment cost and the time required to solve. So as more scenarios we use, more investment costs and time is required to solve. However, if you compare the best stochastic and the deterministic solution, you see the difference in the worst case scenario. Basically, in this figure is the behavior of the stochastic approach for the IEEE 24 bus system. The expected value tends to converge to the solution with the biggest scenario involved. The third test case is the R24, related with the robust optimization over the IEEE 24 bus system. In this scenario, we reach that solution with 3 lines and 1 cable that represents a value investment of $429,000 approximately. In this solution, the robust approach required almost the same time to evaluate the system as the deterministic approach. However, the solution of the robust optimization technique reached a fitness with almost 4 times the value of the deterministic solution, which in the first view can be considered as a not good solution. However, if you consider the robust solution in the worst case scenario, it offered an umbrella protection, eliminating the ruin risk and also turning a black swan into a gray one. So there is a variety of uncertainties that must be addressed, and the renewable share is growing year by year, and its impacts on power systems too. So climate change and weather conditions, as well as many kinds of uncertainties, should be addressed in order to prevent unexpected events. Even if you don't know when the event happens, the most important thing is to be prepared for this one. Related to the approach, Static models are very scenario dependent and consuming a high computational burden. On the other hand, the robust optimization does not require scenario generation, but the robust set can lead to oversized solutions. Thank you.
Okay, Luis, thank you. So I invite people attending the session, the webinar. If you have questions, you can write them on the questions and answers. So let me, well, we have one. Thank you for your presentation. And the question is, did you consider the planning criteria like N-1 and then -2 contingency events or other reliability criteria?
For this study, I didn't use the N-1 or N-2 deterministic study. Related to reliability, in this study, I didn't use any of them. But if we are talking about uncertainties, we should look for the availability of the system, maintenance, and this stuff.
Okay. While we were waiting for some more questions, and we still have some more minutes, let me just ask you to clarify one issue. With these simulations, you use the dynamic model, I believe, not the static one. Yeah.
It was a 10-year planning horizon. So I did a holistic view of the entire planning horizon. And I reached the solutions evaluating all of that.
And the planner has to specify a number of possible additions in terms of reinforcements and corresponding investment values. And the problem is that getting the, let's say, best plan and in terms of allocating possible reinforcements along time and so on.
Exactly. We started with a set list that we already know. And after that, we do the investments based on the object function and its constraints.
Okay, still regarding, perhaps to clarify, because you in several slides you put the objective function in terms of the minimization of the costs, so operation and investment costs.
Okay.
But then one of the initial slides you mentioned the DC versus AC models. So I believe you used an AC model, wasn't that?
Yeah, I used the AC model. The problem was just because my face was on the same place that the object function. So the real object function that I used, it was related with cost and operation. And I used an AC model too.
Mm-hmm. Okay. Well, still no more questions. Let me just ask you a final, perhaps a bit more philosophical one, because one of the big phrases that you used is that you should be prepared to the worst possible nightmare. Should we really be prepared for all thinkable possible nightmares, or should we accept eventually some possible nightmares because they are so costly to be addressed that would be, let's say, not so interesting to be prepared to that, because that would have lots of impacts on the tariffs of lots of investments and so on and so on. That is, do you think it is understandable to accept a certain level of nightmare?
Yeah, I understand it, and I also, yeah, as you said, it's a philosophical question. Because if
well,
you
it's a philosophical
already...
question that has impact on your pockets.
Yeah, exactly. But if you already thought about that scenario, you can plan how it will impact or not. However, if you didn't plan anything, as I can use it as As example, COVID was not planned. Nobody thought about it, and it is impact in every world. But on the other side, when it happened in Texas, the failures, the outages that happened this year in Texas, the FERC and NERC already thought about it, already advised them related that possibility. So they choose the other side, and the impacts, I think, it was way bigger than reinforce the system or just follow what the national regulatory was saying. So based that not transmission, but based the power system is very important to the humanity nowadays. I think the planner should be very, very interested in avoid the risk. And if he can see, he can forecast the risk in any way related with the costs, the power not supplied, the outage could be way more expensive than the simple not reinforce a system or construct a transmission line or in-house or put a generator or substation in the system. I know that transmission lines doesn't create any profit, and who will pay for that? But the other case of the story, the other side of the story, do you want to be in a blizzard for 6 or 7 days if there is that possibility? You know?
Yeah, that's the problem. Well, we have a question here. Congratulations on your presentation. In general, uncertainty modeling considers event independence. I'd like to know your opinion if you think that simultaneity between, for instance, variations in intermittent generation and demand should be considered in studies like the planning, this case expansion planning, and the question also mentions operation, but I believe it's more in terms of long-term planning, in terms of the dependency or simultaneity of some kind of events.
Yeah, it's really important because we're talking about the system that we're going to work and operate for the entire year. And even we are planning for 10 or 20 years, it will be like 8,700 hours multiplied for that time. So it's very important to look each hour of the entire planning horizon and look for not only the peak, but the net peak situation based that we are enhancing the renewable share in the system.
Okay. So we have another question. Thanks for your informative talk. Which type of risks did you consider in your calculations? So in your, I believe in your case studies, because in your presentation you mentioned and you enumerated lots of uncertainties and risks, but in practice, in the simulations that you reported, what kind of risks and uncertainties you used?
In the simulations, I just used the power not supplied. So it was the measure of the risk based that power not supplied should be avoided. So I used that as a measure of the risk of the solution.
So the risk of problems of reliability and the possibility of not supplying the demand.
Exactly.
Okay. Okay, so no more questions at the moment. I think we are approaching the time that we had allocated to the webinar. If there are no more questions, so let me thank Nuno Fidalgo and to you, Luis, for participating and collaborating in this webinar on distribution and transmission expansion planning. I think it was quite interesting and informative, and sometimes these kind of things contribute to counteract some of our beliefs in terms of anticipating investments, in terms of the losses, in terms of the kind of results that the models can provide us. Let me also thank the participants in this webinar, and I believe that if afterwards you have questions, you can always directly contact the authors. So thanks a lot, and good afternoon. Thanks for your participation. Bye.
Bye. Thank you.
Bye. Luis.